Having talked about the mean now for a set of data and a frequency distribution, let's take a look at some of the other measures of centrality here. Next, we can say for a set of data, the median, denoted by the capital letter M, is the middle value of a set of data if after the data has been ordered from smallest to greatest. And the median, one thing about the median that's nice, it's resistant to what are called outliers, meaning that if you have one data item that's kind of out of whack from all the other data, the median kind of disregards that because all we're concerned about is the middle number after we rank it. Now, let's take a look at an example of the median here. It says in slide number 9, in this example, the top news, information, and entertainment websites in May 2000 are shown in the table. Find the median here. Now let's take a look at the data. First we have ZDNet with 9.8 million visitors. And notice here, since these are the top most visited, they're already in order. 9.8 and then 9.6, 9.4, 8.9, and so forth. So they're already in order. So let's think about it. We have what? 1, 2, 3, 4, 5, 6 values. We want to find the middle value. Well, since the sample size is even here, what we want to do is to take the mean of the two middle numbers. So let's go ahead and compute the median knowing that. So since, just remind us here, since the sample size, which in this case is 6, is even, we take the mean of the two middle values after the rank. In this case, they already are, so that's nice for us. So here we have 9.4 plus 8.9, so those are the third and fourth largest numbers. Divide that by 2, and we get 9.15. So this means that in May of 2000, the median of the top 6 websites was 9.15 million visitors. All right, so that's the median. Very good for this idea if we have outliers involved. The median is a really good measure of centrality. Now let's take a look at another measure of center here, and that's called the mode. We can define that by saying for a set of data, it doesn't matter whether it's qualitative or quantitative, the mode is the data item which occurs with the highest frequency. Notice the notation we use for the mode. It's an M with a subscript of 0, M naught is the way that's read. And a couple other constraints on the mode. First, if no data items are repeated, then the data has no mode. And then if more than one data item has the highest frequency, each one of those counts as the mode. So we can have more than one mode for a set of data. All right, let's take a look at another example here. In slide number 12, it says the 9, this is the example we initially looked at, the 9 largest oil reserves measured in billions of barrels are shown in the table. Find the mode. Well, among the data we have here, take a look at it, only the last 2 data items are repeated. So it looks like this value of 29 is going to be our mode. So since 29 is repeated, it has the highest frequency of 2. The mode is 29 for the data. It's the data which occurs with the highest frequency. The mode's a lot different kind of number than the median and the mean. In that we can also use qualitative data to find the mode. It can be non-numerical. We can find the mode of that. And also, we could not have a mode. In other words, existence is guaranteed for the mean and the median, but not necessarily for the mode. And the mode isn't unique either, in that we can have more than one mode. All right, one more measure of several we want to talk about, and that's the midrange. We can say that for a set of data in slide number 13, the midrange, denoted by MR, is the minimum data value plus the maximum data value divided by 2. So it's the average of the smallest and largest values in a set of data. Now, because it uses these extreme values, it's susceptible to outliers. So it's kind of the opposite of a measure of centrality relative to the median, in that it's very susceptible to outliers. All right, let's take a look at an example of how we compute the mid-range when we have a set of data in slide number 14. It says the top 15 countries in internet usage in 1998 is shown in the tables. Compute the mid-range. All right, let's take a look at the data here. Now, conveniently, the data is already ranked for us since it's in a list. The largest data item is 76, and the smallest down here is Finland, 1.6. So there's our maximum and minimum values. So we can use those now to go ahead and compute the mid-range. So let's go ahead and do that now. So for the data, the mid-range is MR, and that's going to be 76.0 plus 1.6, and then we want to divide that by 2. So if we go ahead and do that, let's go ahead and do that on our calculator here. Let me clear out these calculations we were doing before. So we want 76 plus 1.6, and then divide that by 2. And that gives us 38.8 for the mid-range. So the mid-range of the top 15 internet countries in 1998 was 38.8 million. Those were users per week. So notice how the number's a lot larger now. All right. Now, one more thing we want to talk about in this section, and that's the notion of skewness and symmetry. And let me just kind of explain it briefly here, because it's a fairly pretty simple idea. Notice if the data is the same on both sides of its largest class, then we call the data symmetric. Now, it doesn't have to be exactly follow this kind of pattern, but one of these bars can be off, but it doesn't have to be exactly the same on each side. But generally speaking, if it follows this bell shape like this, we call the data symmetric. Now, if the higher frequencies occurs in the lower or beginning classes, we can see in slide 16 that the distribution is skewed to the right. All right, so if I kind of drew a picture of what right skewness would be, it would be kind of like this. If you draw a histogram, if you draw a curve, it would kind of look like that, where the data tails off to the right. All right, so remember what we're thinking about here. This is skewed right. So we can see that the skewness is determined by the direction of the tail and not where the bulk of the data is. All right, so the data tails off to the right, so we say the distribution is skewed right. Conversely, if the higher frequencies occur in these latter classes in a histogram, we say the data is skewed left because it has a left tail. It tails off to the left side. And whenever this is the case, we can see that the mean value is always going to be smaller than the median. The mean is smaller than the median. The opposite is true for right-hand symmetry. All right, so let's take a look at an example here. In slide number 18, it says, um, let's graph this and determine the skewness. Well, in slide number 19, you can see our graph, and we can see that the data tails off to the right. So this data is skewed right.